Hello everyone. Today I'm gonna show you how to calculate lake elevation with DSM Dataset and MODIS Imagery in Google Earth Engine. So now let's get started. So the freshwater lakes plays a vital role in sustaining the ecological balance and supporting the biodiversity and meeting human needs for water supply, agriculture and recreation. In recent decades, the impact of climatic variability and anthropogenic pressures and land use changes has led to a significant alteration in the lake hydrology, manifesting as a variation in the lake surface water area and elevation. So monitoring these hydrological changes is essential for understanding the watershed dynamics and managing the water resource sustainably and formulating the environmental protection policies. The satellite remote sensing offers a powerful and cost-effective means of assessing the surface water dynamics over a large spatial and temporal scale. Among the various indicators used, the Normalized Difference Water Index has proven effective in detecting and delineating the water bodies from multispectral satellite imagery. So NDWI leverages the differential absorption and reflectant property of water in near infrared and green and red band, thereby enhancing the contrast between the water and other land features. So this study utilizes the MODIS surface reflectance product to assess the temporal changes in the selected lake surface water extent for the year 2001 and 2023. So NDWI was computed from MODIS bands to delineate the water features using the threshold based classification. In addition, the ALOS digital surface model was employed to estimate the lake surface elevation by extracting the elevation values corresponding to NDWI identified water pixels. And the 55 percentile of elevation value was chosen to represent the approximate lake surface level while minimizing the edge effects and topographic noises. And further, to ensure the spatial accuracy and facilitate the further analysis, the water masks derived from the NDWI were converted into a vector format. These shapefiles enables the precision estimation of water spread and are instrumental in evaluating the lake boundary shift over time. Moreover, the elevation values within these boundaries were statistically analyzed to derive the changes in lake height, which when compared with the water surface area data, offers an insights of hydrological alterations such as the water volume decline or seasonal inflow-outflow imbalance. So let me get back to Earth Engine. So to calculate the lake elevation with DSM Dataset and MODIS Imagery, first we have to define our region of interest. So to define our region of interest, we're going to define a variable called lake boundary chords. So the chords here represents the coordinates, and this particular variable lake boundary chords which holds the latitude and longitude of this particular study area. So you can able to see here we have this latitude and longitude of this particular study region here. So now to create your study region, so first navigate your region of interest. So my study region lies in close to Kazakhstan here, so you can able to see. So to create your region of interest, first we're going to navigate this option called draw a rectangle. So I'm going to click this option called draw a rectangle. So once you did that, a new options got popped up. So I'm going to select this entire study region. For example, I'm going to select this entire study area. So once you did that, a new variable pop up saying variable geometry here. And here in the top section, we're going to click this option called show generated code. And this particular shows us the latitude and longitude of our newly created study region. So we're going to copy this latitude and longitude using Ctrl+C in our keyboard. And once you copied it, I'm going to close this. And I'm going to paste my latitude and longitude over this particular variable. I'm going to select this part of this latitude and longitude. And I'm going to paste it using Ctrl+V in my keyboard. So once you pasted the latitude and longitude of your study region, so next step we're going to convert this particular variable that is holding the latitude and longitude. We're going to convert this into a polygon. So to do that, we're going to define another variable called lake ROI, that is our region of interest, equals to earthengine.geometry.polygon. So basically this converts our latitude and longitude of this particular variable into a polygon. So we are referring to this particular variable here, lake boundary chords, referring to this particular variable. And in the next step, we're going to center this particular layer by map.centerObject lake ROI, so referring to this particular variable. So now to add this layer, we're going to define. So we're going to define as a map.add layer. And inside, I'm going to mention by this particular variable, that is my lake ROI. So I'm going to copy this and I'm going to paste it here. And next we have to set a default visualization parameter. So I'm going to set my default visualization parameter. This is the default visualization parameter. Next, we're gonna set the output file name, the layer name. So we're gonna mention as a study area. So now I have mentioned as the study area. So in the next step, we're gonna load our MODIS surface reflectance data for the year 2001 and calculate the NDWI, that is Normalized Difference Water Index. I'm gonna reset this. So this is our study region. So I'm gonna turn this off here. So now let us take a look at the MODIS imagery. So Terra surface reflectance 8-day global 250 meter resolution. So the dataset availability is from 2000 to 2025, and the dataset provider is NASA, LP, USGS, and using this particular script you can access this MODIS dataset here. So these are the following bands that is available in this particular dataset here, and the resolution of this particular band is 250 meters. And these are the following bands that is available in this particular dataset, that is surf reflectance B01 and followed by surf reflectance B02. These are the two different bands that is available in this particular dataset, and the scale value and the wavelength of this particular dataset is given, which is ranging from 620 to 670 so 670 nanometers, and this is the surface reflectance band 1, and followed by the second band is the surface reflectance B02. So minimum and maximum value, and the wavelength is around 841 to 876 nanometer. So the surface reflectance band for the band 2. So this particular wavelength, which indicates belongs to red band, and this particular wavelength ranging from 841 to 876 nanometers, which indicates the near infrared band. So let me get back to Earth Engine. So to load this particular dataset, we're going to define a variable called MODIS 2001 NDWI equals to Earth Engine dot image collection MODIS 06 mode 09Q1, and in that we're going to select these two bands, that is dot select function. We're going to use select function here. So dot select surf reflectance B01 and surf reflectance B02. So we are selecting the red and NIR bands here, and we're going to apply the filter function here. So next step, we're going to apply filter it based on a specific timeline. So for that, we're going to use this particular function dot filter date. We're going to mention the year 2001 January 1, 2002 January 1. So this is a specific timeline. We're going to perform our NDWI. For that, we are selecting this particular timeline of 2001 to 2002, and inside we're going to create a loop function. So we're going to create dot map function image, and inside this we're going to create another variable. So basically we're going to apply the scaling factor here, and after that we're going to compute the normalized difference water index. So for that we're going to use this particular loop function. So I'm going to create a variable called scale equals to image dot multiply 0.0001. so this is a scale reflectance value, and followed by we're going to create another variable NDWI equals to scaled, we're referring to this variable scale dot normalized difference surface reflectance B01 and surface reflectance B02. So red minus NIR divided by red plus NIR. So we're going to rename as NDWI, and next we're going to return as NDWI, and last we're going to apply the median function to composite the image using the median function. So that is, we are using the statistical function here. And next step, we're going to define the visualization parameter for our NDWI. So to do that, we're going to define another variable called NDWI visparams, that is visualization parameter, and we're going to set the minimum of minus 0.2 and to a maximum of 0.6. And these are the following color palettes we're going to use it, starting with brown to light green to blue. So blue, which is going to indicate the water areas, and brown, which is going to indicate the non-water areas. So now to add this layer, we're going to define map.add layer MODIS 2001 NDWI.clip based on our region of interest, that is our study region, and this is our visualization parameter, and we're going to output as NDWI 2001. So in the next step, we're going to visualize this NDWI histogram for 2001 with the detailed chart options here. So to do that, we're going to define another variable NDWI histogram 2001. So to create a histogram, we're going to use the specific code here, that is ui.chart.image.histogram, and the image we're going to specify the MODIS 2001 NDWI. And the region I'm going to mention is Lake ROI, that is our study region. And the spatial resolution I'm going to give it as 250 because the MODIS image has a spatial resolution of is around 250 meters. So mentioned as 250 meters. So next we're going to add several options to this particular graph here. So to do that, we're going to define dot set options. And the title I'm going to mention as NDWI, distribution for the lake area 2001. And the h-axis, you're going to mention the title as NDWI value. And you can use this following set of styles here, the title text style and the grid line and the format. And the v-axis, they're going to mention the frequency, the number of pixels, the title text style. So you can use the different style formats given here. And to visualize this particular chart, we're going to mention print NDWI histogram 2001. So I'm going to save this and I'm going to run this code here. So I'm going to click this option here. So now in the task section, the console section, you can able to visualize the graph here. So in the console section, you can able to see this particular graph, that is NDWI distribution for the lake area, the title, the frequency, the number of pixels versus the NDWI value. So we have selected this particular study region here. So you can able to see here. Let me turn on the NDWI value for 2001 here. So this is our NDWI, that is Normalized Difference Water Index for this particular study region. So from this graph here, you can able to visualize this is the number of pixels versus NDWI value. So a lot of pixels that is falling in this particular value, that is ranging from minus 0.42 to 0. So all these pixels which indicates the non-water areas. But after with the value exceeding the 0, that is plus values. For example, this particular set of values which has the value starting from 0.4 to 0.7, which indicates the water areas. For example, this particular lake areas which indicates the water areas. So blue areas which indicates the water area in the study region, which is clearly highlighted in this graph here. So the non-water areas are clearly highlighted in this values here in the negative value, and all the water areas are highlighted in the positive values ranging from 0.4 to 0.7. So you can able to see here. So in the next step, we're going to apply some threshold to identify the water pixels. So basically, we're going to apply a condition if the NDWI is greater than 0.1. So we're going to classify it as a water area. So to apply that threshold value, we're going to define another variable, that is NDWI threshold 2001 equals to MODIS 2001 NDWI dot greater than 0.1. So once you apply this condition, so it's going to basically what it's going to do is it's going to remove all this non-water area pixels, and we're going to create, it's going to retain only the water pixels. So for that, we are applying this particular threshold. So in the next step, to add this layer, we're going to define map.addLayer NDWI threshold 0.1, and we're going to apply this dot clip function lake ROI with the default visualization parameter, and we're going to output as water mask 2001. So now we're going to navigate to the layer section here, and I'm going to select this particular layer. So we're going to turn on the water mask 2001 here. So basically, it's going to leave all the water, the non-water areas, and it's going to retain only the water areas. So you can able to see here. So the white area which indicates the water areas, and all the black areas which indicates the non-water areas. So in the next step, we're going to mask out the non-water pixels. So to do that, we're going to define another variable called water mask 2001 equals to NDWI threshold 2001, referring to this particular variable, and we're going to update mask NDWI threshold 2001. So it's going to do is it's going to retain only the water pixel areas, and it's going to remove all the non-water pixel areas. So to add this layer, we're going to define map.addLayer water mask 2001 dot clip function lake ROI, that is our study region, with the default visualization parameter, and we're going to output as masked water 2001. So let me navigate to the layer section here, and let us visualize the results here. I'm going to turn on this, and I'm going to turn off other layers here. So you can able to see this white area which indicates the water masked water areas. So you can able to see. And in the next step, we're going to convert this water masked pixels to a vector, that is to a polygon feature. So to convert to a raster to a vector, we're going to define another variable lake vector to 2001 equals to water mass 2000 dot reduce to vector. We are applying this function in order to convert the raster to a vector. We are applying this particular function called dot reduce to vectors, and we're going to mention the geometry as Lake ROI, that is our study region, and the spatial resolution to be set to be around 250. And last, to add this layer, we're going to define map.add layer, the lake vector 2001 with the default visualization parameter, and we're going to output as lake boundary 2001. And now let us visualize the result here. So we're going to navigate to the layer section again. So we're going to turn on this lake boundary 2001. So now we can able to see we have navigate to convert the raster to a vector. So this is the lake boundary of 2001 of this study region, Kazakhstan. So you can able to see. So the next step we're gonna use we're gonna load our DEM, that is our DSM dataset, and we're gonna extract the elevation value using the particular DEM value based on this particular lake boundary. So now to do that, first we're gonna define a variable DEM image equals to Earth Engine dot image collection, and this is the code to access this particular DSM dataset. So let me explain about this particular dataset here. So this is ALOS DSM global 30 meter version 3.2. So dataset availability is from 2006 to 2011, and the dataset provider is Earth Observation Research Center. So this is the code to access this particular dataset. So the ALOS AW3D is a global digital surface model dataset with a horizontal resolution of approximately 30 meters. The dataset is based on the DSM data of World 3D topographic data. More details are available in this dataset document. So you can go through this document by clicking this option here. And now let us go through the following bands that is available. So the resolution is around 30 meters, and these are the following bands that is available, that is DSM and STK. So DSM refers to height above the sea level, and signed 16 bits, elevation in meters converted from ellipsoids height based on ITRF 97 and GRS 80 using EGM 96 plus 1 geoid model. And the STK is the stacking number of scene unit DSM used in producing DSM. So the band is derived by resampling the stacking number of 5 meter resolution DSM to 30 meter resolution. So to access this data, we're going to use this particular code here. So let me get back to Earth Engine. So to access this DEM, we are using this particular code, and in that we're going to select this particular band called DSM, that is a digital surface model. So we're going to use this function called dot select function DSM, and to acquire an average elevation, so we're going to define a statistical operation, that is dot mean function, so to get an average elevation. And the next step, we're going to define some visualization parameter to this particular dataset. So to do that, we're going to define a variable. So next step, we're going to set a visualization parameter for DSM data. So to do that, we're going to define a variable elevation vis, that is visualization parameter, and we're going to set the minimum of 0 and to a maximum value of 5000. And these are the following set of color palettes. We're going to use it for a visualization of DSM data. And last, to add this layer, we're going to define map.add layer, DEM image, and with a elevation vis referring to this particular variable called elevation vis, and we're going to output as DEM, that is DEM. And now let us visualize the DSM data of this particular study region. I'm going to run this, and the layer section, I'm going to turn on this particular layer called DEM. So let us visualize it. So it's going to load the DEM data here. So now we can able to visualize the DSM data here, so more clearly. So let me zoom out. So this is the DSM dataset here. So the red areas which indicates the highest level of elevation, and the blue areas which indicates the lowest level of elevations. So this is the color contrast here. So the yellow which indicates the moderate level of elevation. So our study region falls. Here somewhere. This study region, that is you can able to see. So once we visualized our DSM data, next step we're going to estimate the lake elevation as a 55 percentile of elevation within lake area. So to do that, we're going to define a variable called the lake elevation 2001 equals to, so Earth Engine dot number DEM image, we're referring to this particular data, that is DEM image, and we're applying some reducer function here, that is dot reduce region, and inside we're going to mention reducer earth engine dot reducer dot percentile, and we're going to mention as 55. So basically it's going to compute the 55 percentile of elevation value. So this is slightly above the median 50 percentile, so it is often used to avoid the outliers at the edge of lake. And the next step we're going to mention as the geometry, that is our study region. So geometry lake vector 2001 dot geometry function, and next step we're going to define the scale, that is 250, sets the spatial resolutions in meter for our analysis, and we're going to apply dot value and dot get 0. So it's basically it's going to extract the first value from the resulting dictionary of elevation data. So that's why we're going to mention as dot get 0. So it's going to extract the first value from the resulting dictionary of elevation values. And to print this particular data, that is the elevation value, we're going to define print elevation lake elevation 2001, referring to the lake elevation 2001 here, this particular variable. So now we're going to run this and let us visualize the result here for 2001, the lake elevation during 2001, so which is around 338.53 meters. During 2001, the lake elevation is around 338.53 meters. And next step, we're going to export this 2001 lake boundary vector as a shapefile to our Google Drive. So to do that, we're going to define export dot table dot to drive, and collection we're going to refer lake vector to 2001, and the description we're going to mention as lake boundary 2001, and the folder is lake analysis, and the file format is in SHP, that is shapefile. So in the task section, you can able to see here there is an unsubmitted task called lake boundary 2001. So to export this particular data, we're going to click this option called run, and a window pop-up saying initiate table export. So you can export this particular boundary file, that is lake boundary, to your Google Drive by clicking this option called run. And next step, we're going to perform the similar steps here. So to identify the lake elevation during 2001 versus lake elevation during the 2023. So for that, we're going to use this MODIS surface reflectance imagery again, and we're going to calculate the NDWI. So for the year 2023. So now we're going to define a variable called MODIS 2023 NDWI equals to earth engine dot image collection MODIS 061 MOD 09Q1. So through this code we can access the MODIS imagery. And next step, we're going to follow the similar step. We're going to select the surface reflectance band B01 and the surface reflectance band B02. So we're going to select this both bands. So these both bands going to represent the red band and NIR band, that is near infrared band. And now next step, we're going to filter it based on the specific timeline. For example, our specific period of analysis is 2023. So to select the satellite imagery of this particular year, we're going to define dot filter date 2023 January 1, 2024 January 1. So in the next step, we're going to create a loop function here. So I'm going to create dot map function image, and inside this loop I'm going to create a variable. So to apply the scaling factor, so we have to apply the scaling factor here. So you can able to see the scaling factor, which is around 0.0001, which is a scaling factor, needs to be performed before proceeding towards our analysis section. So for that, I'm going to define a variable called scaled equals to image dot multiply 0.0001. And once you applied your scaling factor, in the next step, we're going to create another variable called NDWI to perform the normalized difference water index. To perform that, we're going to define a variable NDWI equals to scaled, referring to this variable where we apply the scaling factor, and we're going to apply dot normalized difference surface reflectance B01 and surface reflectance B02. So this particular function, that is normalized difference, we are applying, that is surface reflectance band B01 minus B02 divided by B01 plus B02. So it's gonna we're gonna finally rename as NDWI, that is normalized difference water index. And we're going to apply this median function to composite the image using the median function to acquire a median image. So you can also apply the other statistical function like mean function. So we are specifically applying median function in order to avoid the extreme high values, the high and low values. So for that, we are applying this with a particular statistical function called median function. And next step, we're gonna add this layer. So to do that, we're gonna define map.addLayer MODIS 2023 NDWI.clip. Based on our, we are applying clip function. Do not acquire the NDWI image based on our region of interest. That is our study region. And now we are referring to our NDWI vis params, that is visualization parameter. We set during the previous steps, we have set this visualization parameter, and we're gonna output the layer name as NDWI 2023. So now let us visualize this particular result here. So I'm going to navigate to the layer section here, and I'm going to turn on this particular image called NDWI 2023. So the image is getting loaded up here, so you can able to see this is NDWI 2023, that is Normalized Difference Water Index. This specific index is used to identify the all water bodies in this particular study region. So we are using this in order to extract the water body for this particular lake here. So you can able to see. So this is NDWI 2023 and this is the NDWI 2021. So I'm going to turn this off here. So this is 2020, this is 2001 and this is 2023. So next step, we're going to create the NDWI chart for 2023. So to do that, to visualize the NDWI histogram for 2023, so we're going to define a variable called NDWI histogram 2023 equals to ui.chart.image.histogram, and inside we're going to define image as MODIS 2023 NDWI, referring to this particular variable MODIS 2023 NDWI, and the region we're going to mention is Lake ROI, that is our region of interest, and the scale we're going to mention is 250, that is the spatial resolution of MODIS Imagery. And to set an additional options to the chart, we're going to define .set options. Title, we're going to define NDWI distribution for the lake area 2023, and the title we're going to mention the h-axis, we're going to mention this NDWI value, and these are the different style format we can apply for our chart here, so you can choose accordingly. And the v-axis we're going to mention the title as frequency, that is number of pixels. And the other set of options, for example, you can define title text style. So for example, you can set it to true in case if you want to visualize it in italic or bold. So this case we are defined as a bold is true. And last, to visualize this histogram, we're going to define print NDWI histogram 2023. So let us visualize the result of in the console section here. So you can able to visualize the NDWI distribution for the lake in 2023. And this is the number of pixels versus NDWI value, and this particular value here you can able to see, which indicates in varies from minus 0.42 to minus 0.1, and you can able to see this particular set of pixel value which indicates the non-water areas, and above the 0, that is positive value ranging from 0.5 to 0.7, which indicates the presence of water. So this set of pixels indicates the presence of water in this area. So you can able to see the absence of water pixels versus the presence of water pixels here. And in the next step, we're going to apply a threshold to identify the water pixels. So basically we're going to apply a threshold, that is if the NDWI value is greater than 0.1, so we're going to consider it as the value. If it is greater than 0.1, we're going to consider it as a water area, and if it is lesser than 0.1, it's going to consider it as a non-water area. So for example, we're going to define a variable called NDWI threshold is threshold 2023 equals to MODIS 2023 NDWI dot greater than 0.1. So if the MODIS 2023 is NDWI is greater than 0.1, so it's going to indicate the presence of water. So to add this layer, we're going to define map.addLayer NDWI threshold 2023, and we can apply the .clip function lake ROI with the default visualization parameter, and we're going to output as water mask 2023. So now let us visualize this particular layer. So I'm going to navigate to the layer section. I'm going to turn on water mask 2023. So all the white areas, now we're going to visualize it. It's going to indicate the presence of water, and all the black areas which going to indicate it as absence of water. So the next step, we're going to mask non-water pixels. So to mask the non-water pixels, we're going to define a variable water mask 2023 equals to NDWI threshold 2023. So we're going to refer to this particular variable here, and we're going to update this particular to mask out the non-water area, we're going to use .update mask function. So NDWI threshold 2023. So this going to result only is going to give us only the water areas, and it's going to mask out all the non-water areas. So to add this layer, let us visualize it. Map.add layer, watermask 2023.clip function, lake ROI with the default visualization parameter, and we're going to output as masked water 2023. So now let us visualize the result here, that is masked water 2023. I'm going to turn this on here. So it's going to load the layer. So I'm going to turn off all of the layers here, so you can able to view that. So you can able to see this white color which indicates the masked, it's going to indicate the water areas, so you can able to see. And the next step, we're going to convert this water mask to a vector, that is we're going to convert this raster to a vector. So to do that, we're going to define a variable lake vector 2023 equals to water mask 2023, referring to this particular variable water mask 2023. And we are applying this particular function, that dot reduce to vector. So to convert a raster to a vector, we are applying this particular function dot reduce to vectors. And the geometry, we're going to refer to lake ROI, that is our region of interest, that is our study area. And we're going to apply the scale to be around 250 meters, that is the spatial resolution of MODIS imagery. And to add this layer, we're going to define map.add layer, lake vector 2023 with the default visualization parameter, and we're going to output the layer name as lake boundary 2023. So now let us visualize the result here. So we're going to navigate to the layer, and I'm going to turn on this particular lake boundary 2023. So now we can able to visualize this is lake boundary during 2023, and this is lake boundary during 2001 versus 2023. So in the next step, we're going to estimate the lake elevation as a 55 percentile of elevation within the lake area. So to do that, we're going to define another variable lake area 2023 equals to earth engine dot number. So we are using to convert the earth engine object to a number. We are applying this particular function number earth engine dot number, and referring to the DEM image, that is DSM, our digital surface model, and we're applying this reduced region. And inside we're going to mention the reducer earth engine dot reducer dot percentile. So it's going to compute the 55 percentile of elevation value. So this is as I said earlier, this is slightly above the median 50 percentile, often used to avoid the outliers at the edges of the lake. So for that, we are applying this particular function earth engine dot reducer dot percentile, and the geometry we're going to refer lake vector 2023 dot geometry, and the scale value is 250. And last, we're going to define dot value function dot get 01. So in order to extract the first value of from the dictionary of elevation stat, so for that we are applying this particular function dot get 0. So in order to extract the first elevation value out of this dictionary of elevation stat. And last, to print this, we're going to define, that is, in order to visualize the lake elevation, we're going to define print lake elevation 2023. And we're going to referring to this particular variable, that is this particular variable lake elevation 2023. So let us visualize it, this one. So we're going to run this code, going to navigate to the run, and going to click run. So now let us visualize the lake elevation during 2001, which is around 338.53 meters, and lake elevation during 2023, which is around 340.51 meters. So based on this observation, you can able to see that a lake elevation during 2001 was around 338 meters, and during 2023 the lake elevation is around 340 meters. So the lake elevation has been improved. So based on our results here, and the last step, you can able to visualize, we're going to export this 2023 lake boundary to our to our Google Drive. So to do that, we're going to define export.table.to-drive collection lake vector 2023, and description we're going to mention as lake boundary 2023, folders lake analysis, and the file format we're going to export as a shape file. So now we're going to navigate to the task section here, and we have two unsubmitted tasks. Previously we have exported the lake boundary to 2001. Now we're going to export the lake boundary 2023. So we're going to click this option called run. So now a new window called initiate table export has pop up. So the task is the lake boundary 2023. So we're going to export to Drive. So you can also export to a cloud storage, earth engine asset, and other exportable areas. So Drive folder, we're going to define lake analysis, and the file name is lake boundary 2023, and the file format is in shape file. So let us run this code. I'm going to click this option called run to export this particular Lake Boundary 2023 to a Google Drive. So now let us wait for the results here. So before that, let us go through the application and the result section of this analysis. So the result is the lake elevation in 2001, which is around 338.53, and the lake elevation during 2023, the value is around 340.51 meters. So the interpretation based on this observation is increased lake elevation over the period of 22 years period. So 1.98 meters it has increased, so which reflects the increased water volume likely caused by the increased precipitation or the inflow, and the decreased evaporation due to the climate change, and the possible activities which indicates the human activities. For example, in case if the lake water volume has reduced, possible causes might be the upstream water diversion or the groundwater abstractions. These are the possible ways the lake water can be reduced. And let us visualize the application section of this particular analysis. So the application is lake elevation monitoring. So it provides an elevation estimate for the lake over the multiple years to assess the surface level fluctuation, which can be linked to the seasonal variability or the long-term climate trends. The hydrological change detection, it identifies the shrinking or expanding lake boundaries to study the drought, glacial melts, or the human impacts on the freshwater resources. And the next application is the water resource management. So it supports the planning and allocation of fresh water in agriculture, industrial and domestic use by providing the timely information on lake storage capacity. And the fourth application is the climate change assessment, which offers an indicator for assessing the climate related impacts in arid and semi-arid zone, where the lake volume is sensitive to the precipitation and evaporation changes. And last is the flood risk and drought analysis. That is, elevation and surface extent changes can serve as an input for flood risk zoning and drought early warning systems. So now let me get back to Earth Engine. So in this video, so now in the submitted section, you can able to see we have managed to export a lake boundary of 2023. So it took less than a minute to export this particular lake boundary 2023 to our Google Drive. So we can go through this particular the vector shape file here. So in this video, I have shown you how to calculate the lake elevation with DSM Dataset and MODIS Imagery in Google Earth Engine. So the code link will be given in the description. So thanks for watching, and make sure that you subscribe to our channel and give us a like.